Alright, so next chapter is aqueous equilibria, where we are going to discuss the concepts of acids and bases. Acids and bases. And we have seen this partly in Gen Chem 1, and we have visited the concept of what acids are, what bases are, and we are going to essentially classify the various different kinds of acids and bases, what various people have done at different points of time, and we'll try to essentially apply the equilibrium concepts that we have learned in the last chapter to an acid-base phenomena. So, think about acids that are common in many foods. If you think about limes and lemons and vinegar, you're thinking about acids. These have sour taste. Acids are also present in a lot of toilet cleaners, grout cleaner, that's actually 6 molar HCl, batteries. Bases, on the other hand, are a little bit less common in food, but they are key ingredients in consumer products like drain openers, antacids. So Drano, that contains sodium hydroxide. Antacids, they work like Tums. That works by basically neutralizing the acidic behavior of foods in your tummy. So we're going to essentially examine different acid-base models in this chapter. All three of those behave a little bit differently. They coexist. One of them is a little bit older than the other two. Some are more modern as far as definition goes, but we will examine through examples for each of these. What we will also do in this chapter is we'll essentially calculate. We'll calculate the pH of a solution and determine the concentration of the hydronium ion. So these are the concepts that we will visit in this chapter. Now, to get you started, when you think about heartburn, you probably think about this painful sensation in your esophagus just below the chest, which is basically caused as the hydrochloric acid, HCl, which the stomach excretes to kill the microorganisms and activate the enzymes to break down the food. And sometimes in your stomach, so if that's your stomach, that's your cardiac notch, this is your pyloric notch, and this is your food, and HCl is going to be secreted by the oxyntic cells, which comprise of the inner lining of the stomach. And the pH of that, believe it or not, is 2. Hopefully everybody realizes lower the pH, more is the acidity, but we will actually visit the entire concept in a much more detail in this chapter also. Now, sometimes, like I was saying, this HCl, it can back up a little bit, and if it backs up out of the stomach into the esophagus, we call this, so it goes back and forth, we call this the reflux or reflux disease, acid reflux, however you want to call it. So an acid, recall from general chemistry. Now going back to the fact why it gives you the burning sensation, of course, when the H plus comes in contact with the esophageal tissue, essentially the burning sensation occurs. Some of the acid can work its way all the way to your mouth, and so you will have this bad, sour taste in your mouth. And so this is something typical that you can expect after a large meal when the stomach is full and the chances of reflux is greatest. So the question is, how do we relieve this? Well, you can relieve mild heartburn by basically swallowing repeatedly. Saliva itself contains bicarbonate ion. So saliva in your mouth that contains HCO3, which is mildly alkaline. So that will react with the excessive acid, and it will neutralize it. Another way that you could do is, to treat heartburn, if it's a little bit more severe, you can use milk of magnesia, Mylanta, Tums. These are over-the-counter medications which contains more base than the saliva does, and hence they would be able to efficiently and effectively neutralize the esophageal acid and relieve you of that burning sensation. Of course, it can become a chronic problem and lead to GERD, the gastroesophageal reflux disease, which is a medical condition associated with chronic heartburn. And of course, now we have developed, as medical researchers, we have developed wireless sensors that can help diagnose and evaluate the treatment of GERD. So those of you who would eventually get into the medicine field would study more about that. But it's a part of biomedical engineering, really. Okay, so let's discuss. Let's talk about the types of acids and bases. And like I discussed earlier, Arrhenius theory, that's the one where we have sources of protons as the acids, and a generalized Arrhenius base is one which essentially generates and dissociates to provide OH negative. So something like NaOH, CaOH whole twice, magnesium hydroxide, anything that has the potential in the structure to give you hydroxide will be called as Arrhenius base. On the other hand, things like HCl, H2SO4, HNO3, something which has the potential to give the proton, is what's called as an Arrhenius acid. This is something you should know from General Chemistry 1. Of course, this classification essentially is restricted to aqueous solutions. It has limitations, and it doesn't account for a lot of different organic substances sometimes, and other inorganic substances like ammonia, which don't necessarily have an OH in the structure, but they do have base-like characteristics. So, for example, one of the characteristics is that bases they turn red litmus blue, and ammonia does that too. But somehow, when you look at the structure, you don't see an OH, so it can't be really classified as an Arrhenius base. And so, for a long time, people were confused what to do about it. And it was not until Bronsted-Lowry's work that they provided the definition of acid and base, where they defined an acid as any substance that can transfer a proton to another substance. So in other words, a proton donor. So in that sense, you can perhaps consider that Bronsted-Lowry retained the definition of an acid as a proton donor. That's what Arrhenius said too. Anything that can give you H+. And Bronsted and Lowry retained that definition that acids are proton donors. But what they defined a base was that a base is a substance that can accept this proton. So proton acceptors will be basic in nature. So according to them, an acid-base reaction was nothing but a proton transfer where proton was moving from an acid to the base. And the products that you get at the end of the day are themselves either acidic or basic in nature as well. So we are going to take a look at what we mean through several examples in the next couple minutes. For instance, if you have a general reaction, HA reacting with some base B. Now, if HA is supposed to be my proton donor, that means it's going to give up H+. Where would that H+ go? That H+ will go to the base. What will be generated will be BH+, and A negative will be liberated in solution. Okay, so again, realize that the proton has been donated by the acid. It has been accepted by the base to give you a new species, BH+, which has been obtained from the base. So what gets obtained from the base is what is called as a conjugate acid. What gets formed from the acid is what is called as conjugate base. Okay, I will tell you a couple ways to identify what is an acid and what is a base, but realize again that A minus, which is produced when HA has lost that proton already, so it's the remaining part of that original acid, and in that sense one can say that the BBH plus and the HA minus, these are the two conjugate acid-base pairs that exist in this equilibrium reaction. Now, the question is, which of the following is a Bronsted-Lowry base but not an Arrhenius base? So which one of these can accept protons but not give you OH negative? This will give OH negative, this will give OH negative. HCl is not even an acid, is not even a base, it's an acid. What's remaining? Ammonia. C is the correct answer. The question next is, write a balanced equation for the dissociation of each of the following Bronsted-Lowry acids in water, and you have to tell me what is the conjugate base of the acid in each case. So you have been given an acid and you have put that in water, right? So now you have H2SO4 sulfuric acid, which is reacting with water. So sulfuric acid is the acid, water is the base. Acid donates the proton, base accepts the proton. What will form from the base would be H3O plus. What will remain will be HSO4 negative. So what becomes of the acid is called as the conjugate base. What becomes of the base is the conjugate acid. So realize the difference between the acid and the conjugate base is that the conjugate base is one proton less. All you have to do is remove one H plus. The difference between base and the conjugate acid is all you have to do is add a proton to the system. We have another one. Now in this case it's pretty simple because we are told that this is an acid. That means the bisulfate is going to act as an acid and be the proton donor, giving you sulfate. And where does that proton go? That proton is picked up by water and it gets converted into H3O plus. So proton donor is going to be our acid, proton acceptor is going to be your base. Compare one way, another way to take a look at this is you compare water H2O to hydronium ion H3O plus. You have added a proton, so it must have been obtained by accepting a proton, and proton acceptors, like we discussed, are basic in nature. What you end up getting is your conjugate acid. Sulfate is your conjugate base. Hopefully in the top two examples you can see that anytime it's a conjugate acid, those have a positive charge. Anytime you have a conjugate base, those have a negative charge. So bases, realize, will always be either negatively charged, or if they are neutral, they will have source of electron, like a lone pair of electron, like in case of ammonia. Acids, on the other hand, will have a positive charge. So here I have hydronium ion, and I'm going to treat that with water again. So this is an acid. It's going to lose the proton, and when it loses proton, it's going to give you H2O. Where does that proton go? That proton is picked up by the H2O to give you hydronium ion. So acid, water is your base. What got formed is your conjugate base. This is going to be your conjugate acid. Likewise, if you want to take a look at ammonium and add H2O to that, loss of proton will give you ammonia. and hydronium ion is going to get generated at the end of the day. So you have an acid reacting with a base to give you conjugate base and conjugate acid. All right, next question is, what is the conjugate acid of each of the following Bronsted-Lowry bases? So these are bases. You have to generate the conjugate acid. That means what happens when you make this accept a proton? You get H2CO3. Again, add a proton. HCO3 with one negative charge, because one positive, two negative, give you one negative. Add a proton. Water, HOH. Add a proton to H2PO4 negative. Phosphoric acid is what is obtained. So again, conjugate acid, if you want to go from base to conjugate acid, add a proton. If you want to go from acid to conjugate base, remove a proton. Now one might ask that if you have an acid dissociation equilibrium, how do you know which direction of the equilibrium does the reaction stand in? So for example, if you take HA, you react it with the base water, how do you know that hydronium ion and A minus would get generated? Because if it's an equilibrium reaction, really, H3O plus can react with A minus to give you HA and H2O back. How do you know which one is going to be more predominant? And realistically speaking, the two bases, the water and the conjugate base A minus, both of those are competing for protons. If water is a stronger base than A negative, that means it's going to accept that proton much faster, and that would mean that your primary products in your reaction are going to be hydronium and A negative. On the other hand, if A negative is a better base, then it's going to react with hydronium ion, and your main products in that case would be the HA and water. So depending on what is a better base, the other side will be the predominant species at equilibrium, because the reaction would have taken place accordingly. So realize that your overall in your overall reaction, the proton is always transferred to the stronger base. We really have to essentially see which of the two, the base or the conjugate base, which of them is a better base. Alternatively, you can look for the better acid, and that will tell you which one wants to remain dissociated. So pick one set and go with that. All right. Again, equilibrium, always, the rule book is equilibrium is going to be in a reaction such that the stronger acid reacts with the stronger base to give you the weaker acid and the weaker base. So if you can make up a call as to what is a better acid or a better base, you will know which direction the equilibrium is going to move towards. So how do we decide on what is a strong acid? A strong acid is one that dissociates completely, like 100%. So things like HCl, for example, HBr, HI, these are strong acids. And so in such solutions, automatically your solution will contain only the hydronium ion and the corresponding conjugate base for that species. Such strong acids, realize that if HI, for instance, if the acid itself is very strong, then the corresponding base is going to be very weak, if this is strong. So then the question is, what is a weak acid? Weak acid is one which is partially dissociated. So let's say you had 100 parts. Out of those 100, maybe only 50 actually go through the dissociation, the rest don't. So you will contain the HA as the more predominant species. So if you have something like, let's say, acetic acid, hydrofluoric acid, nitrous acid, boric acid, these are all examples of carbonic acid. These are examples of weak acids. And The equilibrium will be primarily more towards the reactants because they will not go through a complete dissociation. So very weak acids will have very strong conjugate bases. Hopefully you have realized that in an acid base conjugate pair, if your acid is strong, your base is going to be weak. If your base is strong, your acid is going to be weak. So at any given point of time in the acid-base pair, only one of them is allowed to be strong. Okay, the question is, if you mix equal concentrations of reactants and products, which of the following reactions proceed to the right and which to the left? So you're given hydrofluoric acid reacts with nitric acid or nitrate to give you nitric acid and fluoride. So hopefully you can see, just for the sake of practice, let's also do the proton donor. Acid is the HF. What becomes of the acid is conjugate base. What becomes of the base is conjugate acid. And now the question is, which direction would the equilibrium lie towards? So you really have to play which acid is a better acid between hydrofluoric acid and nitric acid, or which base, F negative and nitrate, which one will be better. And I'll give you a reason for both of them. It's up to you which one you feel comfortable with. Answer will come out to be the same both way. So let's take a look at the acids, HF versus the nitric acid. HF is the weakest acid of all of the binary acids because fluorine, and we will take a mathematical look at that a little later. But all the ic acids for now, just consider all the ic acids, sulfuric acids, hydrochloric acid, hydroiodic acid, nitric acid. These are all strong acids, so these are strong. And this is weak. Another way to take a look is nitrate. If you take a look at the Lewis structure, negative charge from your general chemistry 1, realize that there is resonance, right? And if there is resonance, that means you're going to have a delocalization of the charge. That means that negative charge is not really on one oxygen atom, it's actually spread over all three. So one can say that it's actually 1/3 of a charge rather than one full charge. On the other hand, you have fluorine with one negative charge, a full charge. So which one is a better base? F negative is a better base. So if you have a strong base and you have a strong acid, of course these two are going to react to give you the weak acid and the weak base. So the equilibrium is going to be in the backward direction. Let's take a look at the second one. We have ammonium reacting with carbonate to give you bicarbonate and ammonia. So you have to A, consider carbonate against ammonia, B, consider ammonium, which is your acid, and conjugate base, and that's your conjugate acid. So you have to look at the acidity. So if you look at the acidity of the NH4 plus and the bicarbonate, on one hand you have a positively charged acid, on the other hand you have a negatively charged acid. A couple minutes ago, when I was telling you characteristics of good acids, I said those should have a positive charge. Negative charges usually better bases, and so hopefully you can see ammonium is going to behave as a better acid, and ammonium is going to react with the carbonate to give you the bicarbonate and ammonia. So the reaction is going to go in the forward direction in this case. Now, just to kind of make sure that everybody is on board with the idea, just going to go over a couple more problems. The question is which, or let's say label. Label, okay, what happened here? Label as conjugate acid, conjugate base. So you are given one pair, which is trimethylamine, and the corresponding trimethyl ammonium. There's another one which is H2SO4 with H2SO3. There's a third one which is HNO2 and NO2 negative. Realize we have to have the conjugate acid base pair. Conjugate acid base pair. So conjugate acid means proton donor, base means should have the negative charge. So this last one is a conjugate acid base pair. The first one is actually a conjugate base acid, or you can call it base conjugate acid pair. The one in the middle, it varies each other in number of oxygen atoms, not hydrogen. So those are not a proton transfer type reaction, so no relationship exists between them. Let's take a look at another question. I have two reactions here. We are supposed to label the acid base, conjugate acid, conjugate base. The best way to go about this is compare the two species on either sides of the reaction. So notice for acetic acid, it has lost that proton to become acetate. So this must be your acid because acetic acid is acting as a proton donor. That would mean that water is going to be your base. That would mean that conjugate base is what becomes of the acid. Conjugate acid is what becomes of the base. So this is how you would label. And if you do the same thing in the second example, you can hopefully see that ammonia is the one which is gaining an electron, or rather proton, and so this must be your base. Water is losing that proton, so this must be your acid. Acid gives rise to conjugate base. Base gives rise to conjugate acid. So hopefully you can see, notice, when you look at these two equations simultaneously, you can see that water in one reaction is acting as an acid, in the other reaction it's acting as a base. So water is one of those rare species which, depending on what you put it with, it can act both ways. It's neither an acid nor a base. It can act both ways, as an acid or a base, depending on what you put it with. Such species are also called as amphoteric in nature. So just like amphibian is for something that lives in both land and water, amphoteric is for when it can exist as an acid or a base, depending on what you put it with. All right.